We want to welcome Dr. Lalléchère for accepting this invitation to this meeting. We want to thank Dr. Lalléchère for accepting the invitation to this meeting. We want to give him the floor. So thank you very much.
Many thanks, Dr. Vega, for the kind introduction. Good afternoon, or good evening, or good morning, depending on what place you are now. I do thanks also all the organization committee for this very interesting meeting you were organizing. And it will be my deep pleasure to modestly present some of a selection of what was achieved in Université Clermont Auvergne, so from France, about statistical methods applied in EMC. This is the agenda of my presentation. So first, I will just remind why are we so interested in uncertainty modeling and quantification for EMC or EMI problems. Then I will try just to put the focus on two precise examples given from Aerospace EMC. So first one will be to consider some sensitivity analysis for antennas on EMC systems. And the second one will be dedicated to the case of some field-to-wire coupling on EMC. And some very short words to conclude. So it seems quite natural to figure out why it's so important for us to take into account the variability in electromagnetic compatibility and electromagnetic interference systems. As you may know, for here with picture given from the automotive and aeronautic domain, this kind of problems are most of the time very complex problems. There are plenty of factors that are uncertain due to a large diversity of sources. Can be due to the mass production, aging of systems, or damaging sources, electrical and electromagnetic sources, or sometimes, as you can see here for automotive systems, and the wiring path involved in those systems, it's sometimes difficult to have some a priori about the way all the systems will be organized. So plenty of outputs has to be taken into account. So as I said, it could be due to the different wiring paths that we can encounter, or impedances, shielding characteristics of the system, electromagnetic fields, currents, and so on. It is even more simpler to understand why it's so complicated when you consider inside view of some aeronautics with a large diversity of connectors and also difficulties considering coupling and wiring. This is why it's so natural to, as one of the main target of EMC is to ensure the functioning of the systems. It's very simple to understand why it's so important to provide some tools and precise tools to have a view of the margins that can guarantee the functioning of the systems. And of course, it's also very simple to imagine why statistics and stochastic study can be helpful for this. Another important point, and I will try to illustrate this in the following, is the sensitivity analysis. It could be very interesting for us and for engineers, EMC engineers, to get feedback about what parameters will be very influential in the whole system. So, sorry, part of this are still in French, but everybody can understand. The main idea dealing with EMC is to ensure some margin and security margins. These are some elements taken from a former PhD student at Bourgoisie, who defended his thesis a few years ago. And one of the most important things for EMC engineer is to ensure to get a relevant margin here given with M, considering the immunity level with S and the emission with C. It is important considering sometimes some very wideband frequency range of systems and different levels of perturbation. If you put the focus on a given frequency, you will understand very clearly that statistics and stochastic techniques are very important. For instance, if you you have at your disposal a view of the probability density function for the immunity level, for instance, in blue, and the emission level in gray. You can see that what will happen in between those two probability will be the core for EMC engineer, and it explains why it's so important to get a probabilistic or a statistical view of what happened for the EMC margin. Most of the time, all the work provided by EMC engineer or EMC academics is relying on a lot of work and their experience in the domain to provide some security margins and sufficient security margins. And the idea is here to provide some tools and some idea to get no overestimating of those margins and also not any underestimating of the margins. So this is why it's so important. Just briefly speaking about two methods that will be developed in the illustration that will follow here. One of the most spread technique is the Monte Carlo technique. It is well known because it's rather simple to implement this in your own problems or problematics. You only need to get a view experimental data or numerical data about the black box models that will map your physical issue here. It's quite universal, and it's also very interesting method because it's non-intrusive. For the reason I gave previously, you only need to get your black box representing your model. It is also well known because the convergence can be rather difficult, but one of the main advantages of the method is to enables you to take into account a large number, potentially a large number of random variables and random parameters. The second method I will put the focus on, this is based about works that were initially developed in the EMC group in Université Clermont Auvergne, is a stochastic collocation method. Its basics are rather the same than for Monte Carlo method. It is close to spectral methods and polynomial chaos expansion. The main idea is to develop a design of experiment, but a smart one, choosing very precisely the location of the different inputs you will need in the input random variable space. How those points are produced is quite simple. It depends on the assumption you will have about the input, random inputs you will have to deal with. It could be uniform, normal, log normal, exponential, and so on. Depending on these assumptions, and if you purely ignore what are the intensity or the distribution law needed for the inputs, you can use uniform distribution, for instance. You will have some precise location in your input space. You only need, after all, to use your black box model to compute it n times and to get an output. The main idea is to expand your output quantity of interest. Could be electric field, magnetic field, currents, voltages, and so on. And to use a special expansion on polynomials, your Lagrange polynomials. But you can find also with polynomial chaos, it's well known, other kind of polynomials that can be used. After all, it's quite simple to implement, for instance, the mean value or the higher order statistical moments needed for the interpretation, final interpretation of your the effect of the initial random assumptions. To put it in a nutshell, stochastic collocation is very close to Monte Carlo, as I said, but the main important part is the fact that what is expected from stochastic collocation is the fact that the number of inputs on simulations or experiments is far weaker than what could be expected from Monte Carlo method. Two main drawbacks are well known also. You don't have any mathematical proof about the convergence on the needed number of points. So more or less what is used in the literature is some empirical convergence about the number of points needed with your model. And also we have some limitation because the design of experiments you are producing is you have to take into account the fact that it's a tensor product and you have an exponential increase of the number of points needed. there are a lot of work that were done, not only by your group, but by other groups regarding spectral methods or polynomial chaos, for instance, all over the world. And a lot of research projects that were achieved on this subject. And now we can see that we have a very interesting toolbox using these different bricks, for instance, with stochastic allocation. And it's quite easy to access, for instance, the mean trends of your systems. But what could be more interesting is to get a global overview by practicing the global mapping of the effect of your random assumptions you gave at the beginning, and for instance, the higher orders quantiles or the cumulative density function or probability density function. It could be useful, especially when you are dealing with probability of failure systems or the notion of risk. Could also enrich this whole methodology. More or less, what is, as I said at the beginning, also interesting in this statistical development is the fact that you can provide quite easily sensitivity analysis. More or less, sensitivity analysis is useful to rank the most influential parameters, to calibrate your model, try to minimize the variability, and map what are the most important parameters. Considering what can be explored with EMC or EMI problems, most of the time our configuration are laying emphasis on the fact that influential parameters are not the same as input variables. More or less, the value of H is far weaker than the value of D. And most of the time, we can reduce our problem or our model to 10 or 20, 30 random variables. Even if we can take into account a huge number of random variables at the beginning. And it is one of the motivation for producing some sensitivity analysis. This is a view of a French colleague from French EDF, Bertrand Ios, reviewing what can be expected from sensitivity analysis on the models. And what you can see is that you have a huge diversity of methods that can be useful, but it depends on the computing time or the time you have for experiments, for instance, to provide some, let's say, global indices of your sensitivity analysis. And in the following, I will put the focus on Sobol indices or Sobol-like indices in order to run the most influential parameters. But there is a diversity of methods you can access depending on what is possible for you, considering your own problem. One, as I said previously, mean trends are very interesting for us, but there is still a question remaining, is the way you can identify or try to assess the confidence intervals following the mean trends, for instance, you provided, or the quantile you provided. One quite former method that was used in mathematical analysis and used more recently in electromagnetics is the bootstrap technique. It's quite simple, even it is well known for a couple of years now. And you can find some diversity of methods involving bootstrapping. Jackknife methods, for instance, or inferencing method with bootstrapping. It is very interesting for EMC and EMI because, as I said, some of the time it's quite difficult to have a view of what will be the statistical assumption needed. And it's very important also to couple the results, the final results you will have, and as I said, the confidence intervals that will be needed. The principle is very, very simple. Considering a given population P, you will extract a sample of this with resampling here, with a number here only with 5 items. So the number of items is S here. And the principle is from this subpopulation, you will very simply assess the mean value here. So given here mu, the standard deviation sigma, or for instance, a needed quantile with a given level of quantile, for instance, 95% quantile of your magnetic field if needed. The principle of bootstrap is to provide another time, a given sampling from the initial population, This will give you a new value for mean value, standard deviation, or quantile. And to do this a couple of times. At the end, what will be needed is to provide, for instance, the statistical moments. So, for instance, the mean value of the mean value, or after the mean value of the standard deviation, and so on for the skewness, kurtosis, higher order statistical moments, or quantiles. And at the end, you will have some very useful information about the confidence interval, but only providing what will be needed for you. For instance, to access to the minimum or maximum boundaries needed with 5% quantiles or 95% quantiles. You will have some useful information, for instance, for the mean trend, for the mean value, or for the standard deviation. And very quickly, because it's only a post-treatment of your results. The main efforts were had to be taken considering your experiments, your EMC experiments, or your full wave numerical simulation, for instance. The question that is still open here is the number of times you need to do this. Some authors have provided some view about 100 or 1,000 of resampling, but there is still some work progressing here to improve this this number. But as I said, it's not a problem because it's only post-treatment of data. So a few seconds, for instance. So let's move to the first example I would like to present here. That was treated by EMC group in Université Clermont Auvergne. So it was dedicated to the sensitivity analysis of some antennas embedded on satellites. Most of the context of this work was to put the focus on the increase of small satellite use. And as it was underlined in the past, is the fact that by comparing on providing results involving time domain and frequency domain, you can find, especially for magnetic problems, some difficulties with the use of those kind of satellites. It is all the more important considering, for instance, the Antennas and Propagation Society, where people were interesting their group in the mutual coupling that can exist between the communication antennas and, for instance, the sensors. And it was also the case for EMC because a lot of industrial or subcontractors for the embedding of systems inside satellite are sometimes needing to provide some EMC tests, considering, for instance, the free space testing, which can be rather different, as you can see here on the picture, considering a given level of electric fields, for instance, when all the systems are embedded on the satellite. So the main idea here on the framework for this work was to put the focus on the drift or the variability and the consequences of those variability when considering a given sort of antennas and the potential overcoming that can be involved when considering some drifts. The antennas under consideration was an on-choke antenna embedded on Sentinel satellite. So you got a FECO view here of the satellite. Those kind of satellites are the performance of the satellites were treated fastly. And it's an isoflux antenna, meaning that normally you have to, when considering the radiating efficiency on the antennas, you have to compare with a given level. You are not allowed to overcome here all the flux on the isoflux curve here. So here, this is a view of what can be expected from the radiation pattern in copolarization and cross-polarization. Given some full wave simulation, so here with CST in time domain. And the assumption about the source of uncertainties are summarized here. This is the profile of the antenna. And the main idea at the beginning was to consider that sometimes some manufacturing tolerance may appear about the realization of the antenna. I will put the focus more precisely on the following slide about what are the different random variables that are involved here. Most of the time, what was assumed was 0.1 millimeter standard deviation drifts for a normal assumption about the different random parameters. We were putting the focus on the most important, so it was the center of the frequency bandwidth here, from the most important frequency here, which governs optimization of the antennas. We are laying emphasis in the following on the gain of the antennas on its radiation pattern. Briefly speaking, 4 different classes of random variables were considered. So giving a view, cutting view of the antennas, the first parameters was the height of the number 2 and 4 rings. You can see here. So due to manufacturing tolerances, we were assuming that there can be, because using different tools during manufacturing process, for instance, you can have some variation on this height. So this is the first parameter. The second one is to put the focus also on another tool used during manufacturing with the width of these plates, so plates A and plate C. The third one and the fourth one are more laying emphasis on the problems that can arrive regarding the decentering of sorry. This antenna is centered circularly. You can see you have an actual symmetry circular here, and the X3 parameters is taken from the decentering regarding these 2 rings, and the X direction and the 4th parameters is considering the decentering of these rings and these rings from the center of the antennas. These are the results that were obtained considering a given radiation pattern. So we are here considering a given value of the feed angle, so 45 degrees, on a given frequency, 8.335 gigahertz. And the black curve you can see here is the gain of the antenna. So more or less, this black curve is a deterministic view. What can be expected on where expected from the behavior of these antennas. What is given here is the copperization, the gain for the copperization of the antenna. With green and with red on the green curve, you have 2 results given by stochastic collocation with a given number of points here, and also a given number of simulation of those antennas. And this gives you more or less a caliber. This gives you a maximum caliber and a minimum caliber here from the mean plus or minus 1 standard deviation extracted from the stochastic collocation. As you can see here is the fact that the mean value, the convergence seems to be quite nice regarding the 2 different kinds of design of experiments in red and in green here, given by stochastic collocation, which is the first point. And the other point is also putting the focus on the main interest for us was the sensitivity analysis of this antenna. And this can be given by the standard deviation. And as you can see, this influence seems very, very weak after, let's say, 18 degrees for the theta angle. But between 0 and 18 degrees, you can see there is some dispersion, statistical dispersion of the results. This is for copolarization. Considering the cross-polarization, this can be expected at the beginning, but it's a confirmation here. You can see that there is a very low level of dispersion, even considering the caliber given by stochastic collocation. So same thing in red and in green. And even for this, we can see that we have a good convergence of the statistical results. More interesting case is the case when you put the focus on another observation plane. So it is given here for phi equals 0 degree, same frequency. You can see here the deterministic results obtained with the initial optimization that was provided for the antennas and respecting the isoflux free debit that was expected for these antennas. So in pink, you have the maximum limit that was allowed for the well behavior of the antenna. Also in green here, you have the results that were given by stochastic collocation. So the mean value in the center, on mean value plus 1 standard deviation, mean value minus 1 standard deviation. And as you can see around for theta, around 10 degrees, you have some overcome of the isoflex bound. So this puts the focus on the need to be very careful about what can be expected from manufacturing of the antennas. most interesting result was obtaining cross-polarization, because in black you have what can be expected from the purely deterministic design of the antennas. What was really interesting for these antennas is a very low level gain for cross-polarization, but putting into the problem the random assumption about the random variables, you can see that you have a huge discrepancy with plus 60 dB regarding the gain of this antenna, which was quite interesting because it also put the focus only on 3 given random variables that I previously exposed. So this was the first example. I would like to talk today about sensitivity analysis. Another important point I said was to explore what can be expected from all the methods, especially in non-one. We'll some you can capacity of source that this was a source of. This was provided from a deterministic view here in the paper. As I said previously, giving the mean value on the central tendencies are interesting, but it was a report from our colleague Shoki Kasmi when he was involved with French ENC regarding very different problem about conductive EMC test cases. And he proposed to use the bootstrap to try to have a view on confidence intervals about what can be expected minus at minimum or maximum around the central tendency using the bootstrapping technique. Most important, as I said previously when introducing the aim and the motivation of this work for EMC, is the tails of the distribution, and especially the tails that will be gathered between electromagnetic interferences and the level of susceptibility of those devices. And the idea was to try to know if it was possible to adapt this method that was initially proposed by our colleague Shoki Kasmi for conducting EMC with radiating systems, especially with the satellite I previously presented. So this is a view, this was provided with numerical experiments here, also with CST in time domain. This is a view of the satellite that was reproduced here. The monopole source is emitting some electromagnetic radiation around 0.5 gigahertz. It's made of aluminium, and we were considering also the given two given wiring path here inside the satellite. Most of the random variables were gathered considering 6 uncertain parameters. So the source location, so its location with drift in the X and Z direction. Random wiring height of the cable, considering the height between the cable and on the wall system for the first wiring path and the second wiring path, and also some random assumption considering the two terminal loads that were used here. We put the focus in the following, considering the currents that are measured at these two loads, Z1 and Z2. Briefly speaking, why we were needing some statistical is the fact that the problem was very interesting for us because it was gathering different potential EMC or EMI problems with wiring or some problem with high resonances since we were in an enclosure. And just taking into account what can be expected from a small number of simulation. Perhaps it's not sufficient for Monte Carlo, but we provided 1,000 simulation using CST and the full wave code here, which put the focus on the fact that it's very time consuming and computing those resources is sometimes could be difficult. Just considering the dispersion of the results, you can see here you've got the mean value of the current given on a given load of the system. And the mean value plus or minus 1 standard deviation, you can see that there is a huge discrepancy of results and huge dispersion of results considering one simulation to another. The interest here is to get some confidence interval to have a more, let's say, trustworthy view of what could be expected from the final results regarding the current at the loads. This is here a brief overview of what was provided and in our view of the systems. And we put the focus here on high-order statistical moments. So skewness from skewness third order to sixth order statistical moments, considering here, for instance, the current on the Z1 load at two frequencies. Those two frequencies were not chosen purely arbitrarily because we were putting the focus on two resonances of our systems here. Resonances coming from the wires, so F1, and also resonances coming from the enclosure. We also demonstrate that it was possible to have some trustworthy confidence interval regarding the quantiles of these currents. So 95% quantile of the currents at the two given loads, Z1 and Z2. So this was the result here on the left, given the skewness, the estimation of the skewness of the current at load Z1, considering one frequency, a resonance frequency coming from the enclosure. You can see in black what can be expected from the Monte Carlo. So this is more or less three samples given from Monte Carlo. And the red curve is the view of what is given from the bootstrap, increasing the number of points needed. So you've got 1, 10, 20, or 1,000, because we have 1,000 simulation in the maximal population. So red curve is what can be given by bootstrap, which is quite in a very good accordance with what can be expected from Monte Carlo. And the two green curve are given by the 5% and 95% obtained from the bootstrap, which give you at each step, considering an increase of the number of simulation taken into account, of the confidence intervals that can be expected. This was given for the skewness. The same kind of results were provided from kurtosis, which are very important for a better overview of the statistical distribution of our results, with more or less quick convergence results, because only 30 or 40 simulations were needed. The problem, as it was the case for stochastic collocation, is you don't have any mathematical proof to get a view of the convergence regarding these results. This was proposed in a form of paper considering another kind of test, EMC test here with experimental data, and a given algorithm also provided to minimize and to optimize the number of points needed. The number of points needed considering the population, and the number of points needed considering the resampling needed by bootstrapping technique. These results were also provided for, as you can see, those results were demonstrated as a robust methodology for what was needed, but it also questioned the problem of maxima on more or less higher order quantiles. This was provided for 95 quantiles, so value overcoming the 95 level for quantiles here, and considering frequency resonance of the enclosure, increasing also the frequency here. So you've got two classes of results for the currents obtained on the Z1 impedance and Z2 impedance, with same kind of conclusion here. As previously explained, the result given by the bootstrap is given here in green. So you have the view, let's say, of the mean value of the 95 quantiles of the current, which give you a good estimation of the maximum of current that can be expected. Increasing here, as it was the case in the previous slide, the number of points involved in the bootstrapping technique. And in yellow, you've got the maximum and the minimum interval, confidence intervals that are also given by bootstrap. In blue, you have three different results considering the initial Monte Carlo population. And always in this case, you have very good agreement between the confidence intervals that can be provided by bootstrap and what is expected from given Monte Carlo samples. There are some differences. What is also interesting is to put the analysis more sharply here, and to give the level, more or less the higher order level of the currents, considering the difference that can be expected from the current at Z1 impedances and Z2 impedances. So what is interesting and forthcoming works can be expected considering even higher order quantities, 99%, 99.5%, and so on, and more or less trying to assess the probability of failure of a system. Considering a given threshold, for instance, you are not allowed to overcome with the current at a given load. So this is the end of my talk, and just briefly speaking, because I only provided here a very short selection of what was realized in your EMC group here in Université Clermont Auvergne. So just briefly, we can have we could have also some discussion about what was realized in former studies, considering the demonstration of the interest of some of the methods I previously presented, stochastic allocation, for instance, with experimental data. I mentioned a former PhD student, Thibaut Kouassi. He worked also in the domain of antennas, and there were some collaboration with the University of Adelaide, where some results were provided to improve the design of some wideband leaking antennas. There were also a lot of development considering works with ground penetrating radar, transformer modeling also. This was a collaboration with the University of Zagreb in Croatia, and the use of screening methods for time reversal and the stationarity of time reversal process. There are still some ongoing works I am personally involved in. We are actually providing some alternative techniques to take into account the diversity and the problem of composite materials using Monte Carlo or other techniques. There are still some ongoing works with the University of Split in Croatia regarding maxima and the problem of probability of failure for lightning protection systems with other techniques. And we have some prospects. So it was presented by Shauki Kasmi at the beginning, but there will be, I guess, some very interesting development regarding high power electromagnetics and statistics in the joint event that will be organized next year in Abu Dhabi with 2021 ASEAN Hero event. There is still a French initiative, but also international one now called UMEMA. The last edition took place in Paris in 2020. And a lot of work, especially from Italian colleagues, but not only, are led at the moment regarding the use of fuzzy logic for those kind of problems. There is also one important topic I am personally involved in, some joint collaboration with the TII group regarding Vircator development and uncertainty quantification in this framework. So I thank you for your attention, and I hope I was in time, but I do thank you for your kind attention regarding my presentation.
Thank you very much, Dr. Lalléchère. So we have a few questions from the audience. How to choose the smallest amount of samples to regenerate the statistical analysis with significant information? And there is another question saying, is there a closed expression formula or procedure to determine the number of samples required for the bootstrap method? They're basically the same.
For this kind of question, thanks you for asking. As I said, more or less, what was done was quite empirical. People were providing a number. There is two points. There is the number of samples you will need to provide your assessment, and the number of repetition that will be needed from the bootstrap. The number of repetition is not really the problem because it's only post-treatment, as I said, so it's few seconds. The size of the sample you will use to provide some trustworthy results is very important. And as I said, there were some methodology was provided, and it was a common project with Dr. Shauki Kasmi for some experiments in EMC. So there was a methodology that was basically based on the respect of the Gaussian nature of the different outputs that are provided by the bootstrap, enabling you to define the lowest number of samples that are needed from your bootstrap. I can't see because I have some question, direct questions. There were a question about the fact that many problems does not have any Gaussian PDF in EMC. And how does the bootstrapping behave in such a case? What about the non-regular function with wide frequency band analysis? I do thank you for the question. Yes, it's a very relevant question. More or less, you can try to provide here. I don't speak about really regarding the bootstraps, the assumption. Most of the time, what I presented with Gaussian assumption was about the antennas problem at the beginning. And it was with stochastic allocation. And as I said, it's possible to take into account different assumptions. Regarding the bootstrap, you don't have to consider especially Gaussian nature of the resampling needed. Most of the time, it's you don't have those kind of interest here. What you will have at the beginning is, for instance, an experimental or a numerical experiment, so some full wave simulation, for instance, considering given assumption about your parameter. If you have an ID, it's uniform or exponential or variable low distribution, you will provide your experiments, and bootstrapping will only provide you some interval confidence. You don't have, you just need to have the experiments. You don't have to put low distribution during the bootstrapping.
Okay. Okay, I think this answered the question, just one of the last questions about the Gaussian nature of the distribution. Yes, and finally we have here another question asking what is the disturbance value diagram of two PDFs? It is amplitude of energy or other.
So sorry, the question is about the nature of the output, or
what is the disturbance value diagram of two PDFs? Is it amplitude, energy, or other? So
okay, more or less it depends on your issue. If you have, because of the standard, some view of the distribution of and in a certain point, it's very difficult sometimes to access those kind of information. You have a lot of guidelines that are available when dealing with lightning, so it's very useful and very convenient. For instance, regarding the statistics, because there are a lot of experiments, but sometimes it's difficult to have a clear view of the probability distribution, both of the emission level. So, okay, this could be energy, this could be electric fields, this could be currents or voltage, for instance, and also very difficult to have the probability distribution from regarding the immunity of your systems. But it's a part of the uncertainty quantification. So the first step, and it is very important, is to have a sufficient number of experiments or simulation to have, let's say, a more precise view of those information. But more or less, this can be depending on what is available for you. Those parameters can be energy, electromagnetic field, and so on, depending on what is available.
okay, okay. Thank you very much, Dr. Lalléchère.
My pleasure, thank you.
Interesting talk, very comprehensive, and we had a lot of good questions in the audience. I think the topic is a topic of interest for many people in this field. So thank you very much again.
You're welcome. Thanks.
Yeah. Okay. So.